Hi, welcome back to a new IMONST 2 video. So in this video, we'll be talking about IMONST Senior Problem 5. So this is quite a hard one, to be honest. Now let's look at the question. Let p and q be real numbers such that the quadratic equation x squared plus px plus q equals to 0 has two distinct real solutions, x1 and x2. Suppose that x1 minus x2 absolute value is 1 and p minus q into absolute value is also 1. Prove that all of p, q, x1 and x2 are integers. Okay, now we can basically turn our x squared plus px plus q equals to 0 into something like this, meaning x minus x1 then times x minus x2. These two are the roots, because if you put x1, if you substitute x with x1 or x2, the whole equation becomes a 0. One of these terms becomes 0 and then the whole thing becomes 0. Okay, so x minus x1 times x minus x2 equals to 0. So again, because the order of x1 and x2 does not matter because they are still unknown, so we can write WLOG, meaning without loss of generality. So WLOG, let x2 be larger than x1, okay? So that x1 minus x2 is actually -1. And then x1, x2 is equals to x1 plus 1, okay? So that with this, we can make a bit of a substitution later on, okay? Now, let's see that, we can see that we can expand this and turn it into x squared minus x1 plus x2x, and then plus, because two negatives make up a positive. So we have x squared minus x1 plus x2x plus x1 x2 equals to 0. Now, from here, we also know that this p corresponds to negative x1 plus x2. And then we also can substitute x2 equals to x1 plus 1. So equals to negative 2x1 plus 1. And then q itself, q would become x1 times x1 plus 1 equals to x1 squared plus x1, okay? Something like this. Now, sorry guys, I took a little bit of a break, but let's continue. Okay, so we would have p being equal to negative 2x1 plus 1, and then q would be equal to x1 squared plus another x1. Now, from this one, we know that just now, as our title has told us, that p minus q into absolute equals to 1, right? So we can divide this into two cases actually. So the first case would be p minus q. Okay, this is the original one. P minus q absolute equals to 1. We can divide this into two cases. So let's divide it. So the first case would actually be p minus q equals to 1. And then this one would be p minus q equals to -1, which means we can turn it into q minus p equals to 1 because we're just reversing the values. So for this one, we would have negative 2x1 plus 1 minus x1 squared plus x1 equals to 1. Now, because both of these are negative, we don't really like it, so we can just inverse the value. So we would have 2x1 plus 1 plus x1 squared plus x1 equals to -1, as we can see here. Then we can add both sides by 1, okay? So we will have x1 squared plus 3x1 plus 2 equals to 0. Now, this thing can be further broken down into x1 plus 1 and x1 plus 2 equals to 0. So we would have x1 equals to -1, and then we will also have x1 equals to -2. And then from our above assumption of x2 being x1 plus 1, we will have x2 equals to x1 plus 1, which is -1 plus 1, which is 0. Then for this one, x2 would be -1. Now, so this is the first case. I'll settle p and q later. So for the second case, we have q minus p equals to 1. We will have x1 squared plus x minus 2x1 plus 1. So this thing is a whole bracket equals to 1. Then we minus 1 on both sides. We will get x1 squared minus x1 minus 2 equals to 0. Now, for this one, we can further break this down into, you don't need the quadratic equation. You can just break this down into x1 minus 2 and x1 plus 1 equals to 0. Now, for this one, give me a moment. We would have a x1 equals to 2 or x1 equals to negative 1, which is the same. So for this one, we will just have x2 equals to x1 plus 1 equals to 3. Okay, so for these, we have collected 3 solutions. Okay, so we have set 1, set 2, set 3. Let's make a tiny graph, I guess. So something like this. And then we have x2 also. x2 equals to x1 plus 1. And then p equals to negative 2x1 plus 1. Then finally, q equals to x1, x2. Okay, so we would have x1 in the first set would be 1, and then this is 0. And then set 2, we would have x1 equals to negative 2, x2 equals to 1. Then for set 3, we would have x1 being 2, and then x2 equals to 3. Okay? So what we will have here, p equals to negative 2x1 plus 1, which is negative 2 plus 1, then negative 2 plus 1 is negative 1, negative 1, negative 1 is just 1. Then this one, negative 2x2 plus 1, this is 3. And then this one would be negative 5. Then for this one, q would be 0. For set 2, q would be 2. And for set 3, q would be 6. Okay? Now, so from what we've concluded here, all of x1, x2, p, and q, all of these are just integers. So what we will need to write here is that what we can write here is, I'm not sure if this is correct. If anyone thinks there's a better way to write, you can write it down in the comments below, because this is just me stating out my own way of writing this proof. The only possible quadruple sets of p, q, x1, x1, x2 are, so we have 3 sets, right? Just list them out. So what we have here are negative 1, 0, 1, 0. Then for the next set, we will have negative 2, negative 1, 3, 2. And for the final set, we have 2, 3, negative 5, and 6. Okay. Hence, the all of p, q, x1, and x2 can only be, what are those? Those are integers. So given our whole process of doing this stuff, then what we've solved over here, we find out that all these numbers are integers, and then yeah, we're basically done. I am not sure if this is the best way to write it. If you guys have any suggestions, please do write down in the comments below. I really appreciate constructive feedback. So yeah, I think this is the video for today. It might be a bit abrupt, but I apologize for that. Yeah, and this is it. So kind of admire this whole process a little bit. I don't know, can kind of pause a little bit. Yep, this is it. So we'll see you guys in the next video. Ciao, ciao.